In this video, we'll explore the gamma distribution. So we're just going to go through everything. So a random variable x is distributed as gamma with parameters k and theta, where k and theta are both positive numbers if it has the following PDF. So the PDF is of this form. We have, again, f big X little x is equal to 1 over, and this weird symbol will be explained later in just a second. It's called gamma, so the gamma function. So 1 over the gamma function evaluated at k, theta to the power k, x to the power of k minus 1, e to the power of negative x over theta, as long as x is bigger than or equal to 0, and 0 otherwise. So it's only defined on the same range as the exponential function, and we'll see the relationship between exponential and gamma at the end of the video. Okay, now the elusive thing here, the thing you probably don't know, is the gamma function. So the gamma function is defined as an integral. So it's simply defined as the gamma function evaluated at some real number t is the integral from 0 to infinity x to the t minus 1 e to the minus x dx. And that's it. It seems kind of complicated, but it's just defined as this integral. So it's just easier notation than if we had to put this whole integral down here. Okay, cool. So let's do the expected value, variance, and MGF, all of which I've calculated already to save us some time. So expected value of x is given by, well, the basic expected value formula. It's integral from 0 to infinity, since that's where it's defined to be non-zero. We just put the PDF right here. We put an extra x dx. So I'm going to pull out. Now notice something interesting. You might freak out at first because you think, oh no, this gamma function is an integral and it's inside another integral. That's going to be very hard to calculate. Well, the thing to notice is that this integral right here is dx. And this gamma function is a function of k. So it has nothing to do with this x at all. So we can just pull it out. Likewise, this theta to the k has nothing to do with the x. We can just pull it out. So we'll just pull them out right here. We're left with this part inside. So this x to the k minus 1 and this x I've combined as x to the k, e to the negative x over theta. Now we make a u substitution. U equals x over theta, du equals 1 over theta dx. And we do the u substitution, we substitute everywhere there's an x, we would put u theta, so we do all that. And then we get this result right here. And we get a nice cancellation of theta to the k on the bottom, and I'm going to call this c. What's remaining? So it's going to be theta over gamma function at k. That's going to be our big C, just a constant, just for renaming purposes. And then what we get is we have u to the k, e to the negative u, du. So now we have to do integration by parts, and I've given the what you should put as v and dw. And then over here, this way you get the same c over here. You get integral from 0 to infinity, e to the minus u, k, u to the k minus 1, du. So let me see what happened. When you do integration by parts, you have vw, so you have u to the k, e to the negative u, evaluated from 0 to infinity. This is a pattern we've seen many times in the past. If you put infinity into here, so what we're dealing with is the product of this guy and this guy. If you put infinity, this will be in the denominator, this e to the u will dominate and become 0. If you put 0, it'll be 0 to the power k, the numerator will vanish. So either way, this is 0. So all we're left with is, it's really vw minus integral w dv. So since the vw vanishes, we just have integral w dv, which is exactly what I've written here. Okay, so now that is written right here. This k is a constant. We can pull it out. Nothing to do with u. And now notice something interesting. This e to the minus u, u to the k minus 1, is exactly the gamma function. So instead of u, here we have x. So it's x to the t minus 1. Here it's u to the k minus 1. Here it's e to the negative x. Here it's e to the negative u. So it's the same thing. So this whole thing is really k times the gamma function evaluated at the point k. And I notice this c is the theta over gamma to the k. So this gamma to the k cancels with this gamma to the k. So we just have theta k. So the final answer is theta k for the expected value. Okay, now we'll do the, this is the variance. So the variance, we're going to use the typical variance formula. Here we have this, we just calculated previously. So we need to find expected value of x squared. So I've written the definition by definition what it is. We have x squared times the PDF. And this c is a constant I've taken out as 1 over gamma to the k, theta to the power of k in the denominator. That's taken over here. And we have x squared, x to the k minus 1 combined to make x to the k plus 1, e to the negative x over theta. We're going to use that same u substitution, and doing that we have, coming down here, we have this quantity right here. So now we have everything in terms of u. So now we can take this theta to the k plus 1, and then we have another theta, so it's theta to the k plus 2. And the c, part of the c, we had theta to the k in the denominator, so we have theta squared over the gamma function at k. So that c, I've kind of opened it up and said what it really is, so now here's our constant right here. So now again here, we're just going to do the same thing. We're going to use integration by parts using very similar choices, just instead we have a k plus 1 instead of a k here. So we're going to do all that. Coming down here, again, the VW term goes away when we take it from 0 to infinity. So then what we have is this right here. This is just the WdV term, the integral of the WdV term. So then that's all here. And then we have theta squared over the gamma function at k plus 1. And then this, notice this guy. About this guy, the thing is that if we look at when we were calculating the expected value, we see that the same thing is right here. So notice here we have u to the k, e to the minus u du from 0 to infinity. Here the same thing. We have u to the k, e to the minus u du from 0 to infinity. And using integration by parts there, we found that was k gamma function at k. So likewise, I've written here, we have theta squared over gamma to the k plus 1 outside, k gamma function at k. These twos cancel right here. And we have k times k plus 1 times theta squared. So that is just this. Now we have to remember to subtract k squared theta squared. So doing that, we get k theta squared as the variance of our gamma distribution. The last thing we got to do is find the MGF. So the MGF is very interesting in that it's pretty easy to calculate based relative to the other two things. So by definition, it is the PDF times this e to the sx term. So I've taken out this constants already, and this e and this e, since they're both e's, we can just add their exponents, and we have this. Now let's do a little bit, let's just kind of get a key insight what's going on here. Okay, so now continuing that, I've written the MGF in a little different form. So I've taken the e terms and I have put them together and I've rewritten them in different forms. So just confirm for yourself that from the previous statement to this current statement, this e to the power of what this is the same as what e to the power of the previous thing was. Okay, so I've written it in the suggestive form because I want to think about this distribution. Think about a distribution which is gamma with parameters k and theta over 1 minus s theta. Now what would the PDF of that look like? Well, it would look very similar to this. It would be x to the k minus 1, e to the negative x. Remember, it's negative x over theta. So since theta in this case is being played by theta over 1 minus s theta, it's going to be negative this guy, negative x over this guy, which is exactly what we have here, since it's negative x times is the reciprocal of this guy. Okay, except what we don't have, this is, we don't have the constants, so we need to remember the constants. Okay, and speaking of those constants, actually we need to put 1 over gamma to the k, theta to the k, since those were there from the previous statement. And now, so this would be 1, because it's integrating over the whole, over all the places it's defined of this gamma distribution. It would be 1, except we have to remember that it's 1 times the constant, since it's not the pure, it's not this pure PDF, it's the PDF divided by the constants. So we need to, this would be 1 over gamma evaluated at k, theta to the k, gamma of k, and the other constant would be theta to the power of k. So theta in this case is being played by theta over 1 minus s theta. So it's theta to the k over 1 minus s theta to the k. Now we have lots of nice cancellations right here, so we just have 1 minus s theta to the negative k, since this is in the denominator. So notice that this is our MGF, except we have one little caveat that we have to deal with. Theta, remember, we had to say was greater than 0, which means that this guy right here, this thing right here has to be greater than 0. So we see that that's true only if, well, theta is definitely greater than 0. It came from a distribution where theta was the actual theta. So it's only true if 1 minus s theta is greater than 0. So we need 1 minus s theta to be greater than 0. Just manipulating a little bit. 1 is greater than s theta. We need s is less than 1 over theta. So that's a restriction on the kinds of s's we can put in there. So s must be less than 1 over theta if this is to work out. Okay, so this is our MGF. And the last thing we'll do in this video is we're going to talk about how the exponential distribution we talked about in a previous video is just a special case of this. So the special case exactly is, consider the gamma distribution where k is equal to 1, and instead of theta, we're going to have 1 over lambda play the role of theta. So now let's see what happens. Writing the PDF, we're going to have x to the k minus 1, so it's going to be x to the 1 minus 1, e to the negative x over theta, so in this case it's going to be e to the negative x lambda, and of course don't remember, we have to remember to do the constants. So we have 1 over, and what is the gamma function evaluated at 1? If you plug it into the definition, you're going to see that it's going to be 1, and then we have theta to the power of k, so that's going to be 1 over lambda to the power of k, and k in here is 1, so it's going to be lambda to the power of negative k, and since k here is 1, it's lambda to the negative 1, which is just 1 over lambda in the denominator. So flipping it again, we have, this is lambda, this guy right here is just 1. It's going to be lambda e to the negative lambda x. X is greater than or equal to 0. And we see that's exactly the definition of the exponential distribution. So it's actually very interesting how this is a special case of the exponential distribution. And when we talk about, when we talk about chi-squared random variables, or if you go to that video, you're going to see that chi-squared is also a special case of the gamma distribution.